Good morning, everyone. Happy Monday. Go ahead, let me know who's in the chat right now. Looks like two people, maybe. Just so you guys know, I'll talk about the calendar. So the calendar's up. You guys can go ahead and open that up. How was everyone's weekend? Hopefully pretty good. Pretty good. What about yours? Oh, good to hear, Hunter. My weekend was it was all right, uneventful like every other weekend, but it was fine. I kept myself busy. Yeah, it was. I watched some TV, played some video games, got prepared for this week, all that good stuff. Nothing new though. Getting, I guess, used to this whole situation a little bit more and more each week. It's not ideal, but at least I'm getting used to it a little bit. It's gonna really start being painful once weather gets really nice. Like even yesterday was pretty nice out, so I was like going outside. I was like, man, this is great. I wish I could actually do something instead of just like roam around and avoid everyone. So hopefully soon we can do that. I'll give it a little bit of time. Looks like we got two people. I'll give it like 2 more minutes, see if anyone else pops in. Hunter, you still got to convince Cole. It's okay, I understand. Good morning, Rachel. How's it going? How was your weekend, Rachel? I think for a lot of people, the weekend's just meshing into the week, anyways. People don't know what month it is, don't know what day it is. Pretty boring, yeah. Yeah, I understand that. It's just hard. Like there's only so much you can do like with your time. It's hard to like keep motivated and keep like interested in something. Okay. So it looks like maybe it's you three again, and then Cole probably isn't here. So if you guys haven't yet, open up your calendar, the BC calendar. I'm going to talk about that, and then also College Board. I'll go through the answers for the College Board assignment because I don't know if I did or not. If I did, just tell me, and I don't have to go over it. But I can't remember if I did or not. Okay, so I'm going to get started. Today, actually, we're learning something new. So this is going to be. Oh, we did go over the answers. Okay, then I don't have to do that. Cool. So today is going to be the actual last day of BC. Like this will be the last topic you learn in BC. So we'll get to that. You guys can see we already reviewed the College Board, so we don't have to worry about that. We have we're going to learn about logistic models today. So we'll go through those notes, kind of teach you. Nothing really crazy with those. It's not anything brand new. It's kind of just adding an extra element to exponential growth. So we'll talk about that. If you noticed, we're not streaming Tuesdays and Thursdays. Okay, in fact, not just are we not streaming, we're not doing anything Tuesdays and Thursdays. So I talked to you guys last week. I think I mentioned this, but now it's kind of more official. So we were told that it's better off for us to focus like daily for our topics, meaning like history, science, math, English are all going to kind of have their own days to do stuff. So that way you guys aren't overwhelmed. You guys aren't like scrambling, doing assignments all the time and like losing your minds a little bit. So I want to adhere to that as much as like, what we do in here anyways isn't, I don't think, taking up like a whole lot of your time. This will allow you to, if you want to, you can sleep in Tuesdays and Thursdays. You can spend time writing a paper or like whatever it may be. It just kind of gives you that flexibility. And for you guys, I'm really not worried. And the reason why I'm not worried is because, first of all, the AP test, as far as I understand, it's still up in the air because I still kind of misunderstood it maybe a little bit. But from what I understand, it seems like it's going to be a free response question or like a set of questions, and it's like 45 minutes long. So like your entire AP test is going to be just that, just 45 minutes long of a free response question. So with that being said, I mean, I don't think that there's any point of us doing review every single day of the week because first of all, we're already almost done with all the review we need to do anyways. We've already almost got entirely through AB. So I'm just not like super. I think we're gonna be fine because I don't think the test is gonna be till probably mid to late May is what I'm guessing, and at least the first option. And if you wanted to, you could probably wait till June to take it too. We'll see what they come out with, but I think that I think we're gonna have plenty of time to get through everything we need to get through or want to get through. So I don't feel like any need to like overwork you and to work every day. So with that being said, basically really 2 days a week is what we're supposed to do. I'm gonna give you guys an assignment Friday. I don't know if it's going to be an assignment. Like honestly, I might assign it I might assign it Wednesday or Thursday, and it'll just be due the next week. So it'll give you guys the option, like, oh, if I know about it Wednesday and it's due next Monday, you guys can just do it, knock it out. So like you don't like feel like you have to do it just Friday, because Friday's supposed to be a review day. That's the idea, is that Friday's going to be spent for all the teachers to just like not assign anything, not teach anything, just kind of like be available to review any material from the week that students have questions on. So the way we do it's a little bit different. I mean, we review it anyways. Friday will be spent just reviewing anything throughout the week you want to go over. But then also, like I said, I'll give you an assignment that you can do Friday if you so choose. So like I'll do my little my stream. Actually, I need to change my calendar. So Friday, like usual, I won't be doing the office hour live stream. I'll just be doing like a normal 9 to 10. So I'll be here, like just sitting here. If you guys want to hop in and you guys can do like for Friday, the Unit 7 FRQ. If you want to just get it knocked out right then and there, that's absolutely fine. If you want to do it earlier, that's fine. I'm just gonna leave it up to you guys. So that's how things are gonna go from here on out. Like I said, I should know by Friday more details on your AP test. I'm gonna get exact, formats of what's going on. Although they have a pretty good idea, maybe I'll get more information on that. So just based off of that, we'll see. I don't think I'm gonna give you guys any assignment over spring break. So if you didn't realize, spring break is next week. So I don't see any point of giving you guys any assignment. If you would like me to give you an assignment, I can, if that would help. If not, My recommendation would be watch some of the videos that AP has released. So their YouTube page has been doing videos. I don't know how often, but they've been doing it pretty often. Like today, I know like right now they have a live stream going on for I think series, like the beginning of series. So if you guys were like interested, maybe over break, you can touch up on some topics by watching some videos. But I'm not going to give you guys an actual assignment. I don't think. So you guys will get to enjoy your spring break, well, as much as you can. Okay, so I think that's pretty much sums up what I want to talk about with the calendar. I'll give it a second. Does anyone have any questions you guys can put in the chat on anything? Nope, nothing for me. Okay, cool. So with that being said, then let's look at you guys said we went over the multiple choice questions, so you're fine with that. So with that being said, let's get started with the notes. So I'm going to switch cameras here. And this is going to be the title of your section, Logistic Models. That's what we're going to learn about today. And I just wrote this idea, this population growth. That's just like a general way to represent population. So if you guys can, just copy that stuff down, and I'll get started on the notes. Okay, so probably have that copied down now. This representation, this NFT, this isn't something like we need to memorize. This is just a general expression for maybe showing population growth. So my question for you guys, and I want you to answer this in the chat. Is this a realistic model? So I know we use that as like a way to represent exponential growth, or exponential. Well, yeah, in this case, I guess it's exponential growth. So I want to ask you guys, do you think this in real life? Is this a realistic equation to be working with? Like think of in your own heads as like a made up situation, and this was the equation. Would it make sense? That's my question for you. I don't know how much of a delay it is, so not really sure. LOL. It probably gives a decent approximation, but we can never know the true population for most creatures. Okay, I mean it looks similar. Okay, so let me clarify a little bit. I would agree, Liberty, with what you said. It probably gives a decent approximation. We can't really know a true population. That's 100% true, and that's kind of what I was getting at with my question. So if I were to think about a situation, I mean, you can just insert animal or organism here. This would be the population. This would be their initial population. So at time 0, what are they at? This is obviously an exponential. the rate of change. So at what rate is the population changing, and then obviously t is time. So this model is like fine. Let's think about like rabbits. Okay, let's put rabbits in like the wild. We all know that they populate very quickly. So it makes sense that they definitely have an exponential growth. 2 turns into 5, which turns into 15, which turns into 40, and so on, right? And so that's exponentially growing. But one thing that we don't see in this model is the fact that this will grow forever. Okay, so you think about that. Like in the real world, right? If we had a model that was exponential, it's going to grow forever. There is no horizontal asymptote. Nothing prohibits it or inhibits it from growing. Okay, and then there's people that kind of, we started off with this differential calculus and, we talked about exponentials. And, way back in the day when this stuff was first starting to be discussed and worked on, they were thinking to themselves like, okay, in the real world, this doesn't make sense. Just like the population of people doesn't grow exponentially forever. At some point, there's a cap. And how do we define that cap? Well, that cap's defined by what's our threshold? What's like the maximum population we can get to? And there's a lot of things that play a part in that. The biggest thing is just resources. If you have a million bunnies running around in like a very small area, there's not going to be enough resources for them to survive. Okay, they're going to be competing for resources and they're going to die out. Hopefully they don't turn cannibalistic or anything like that. Barring that, assuming that they don't start doing anything crazy like that, they're gonna run out of food. Okay, and then once they all run out of food, they all die. That's a realistic situation that could happen in the real world, and it has happened in the real world. It's happened to people. It's happened to a lot of different situations. I actually think I don't know if this is 100% true, but I think I heard this before. Easter Island. Is it Easter Island? It's one of those like Easter Island or like where the Stonehenge is, wherever that place is. One of those like important, I guess, landmarks. I think there was like a population that was there, and they were cultivating the land and like it was really prosperous. And then they were chopping down trees and they did too much. Like they took down too many trees. They used too many resources. Next thing they knew, they had nothing. There was no food, no land, no animals, nothing. So like they were completely starved out. I think there was actually like a Dr. Seuss book on that too. I can't remember what it was called. I remember watching the movie though. But yeah, like they chop all the trees down, and then animals start dying out, and blah blah blah. So that's what realistically happens in the world. This equation doesn't model that. So the idea of a logistic model is to account for that. It's to account for certain factors that inhibit exponential growth or exponential decay. So like basically saying like, okay, if a population hits this point, if a population gets down to 12 bunnies, it's only going to go, the Lorax. Yeah, exactly. Yeah. But yeah, these thresholds, not only for exponential growth, but which we'll focus on, but also decay. It's the idea of like if you get any higher than this, everything's going to die out. If you get any lower than this, everything is going to die out. So what it is an asymptote. It's an asymptote that's going to prevent growth or decay. Okay, so the question then I guess is, well, how do we represent this? So I want to start off by looking at this equation. So dn dt is equal to r times n. So this is going to be my rate of population change. So we have a differential equation there, right? A derivative is equal to r times n. R is going to be, in this case, our coefficient. So that's going to be something it's a proportional. I think sometimes it's called the constant of proportionality. Maybe that's what you guys have heard last year when you learned about it. It's just a way to relate the rate and the actual population. So how do those two go together? So for example, you have 5,000, 5,000 cows. They're changing at a rate of 4/3 cow per hour or whatever. So your rate of proportionality would be 4/3, the number of cows 5,000, and then your rate of change represented by that. Okay, so this is just a way to represent the rate of change of the population. Your rate could be negative, so that means like things could be dying out. or a fraction. So this is just like a general way to express this. Now, the question is, how do we adjust this so we can have that inhibiting growth? So how do we inhibit this growth? Again, this rate of change is going to only increase or only decrease, and it's going to keep doing that over and over and over. And like we talked about, that's not necessarily realistic. So let's look at the equation we want to use. All right, so we have this equation dn dt equals r times n, so we maintain that, but then they're multiplying times 1 minus n over k. Okay, so this specific example, I'm dealing only with population. Population isn't the only thing that logistic models deal with. They deal with anything that has to do with exponential growth. Okay, so this is we're just talking about this example. We'll talk about more generic examples, but I think population for the most part is what you'll see in this class. Okay, so we have this right here. All right, this is a way we can get a limiting factor. I'll talk about each piece. Big variable is k, so that's really the only new variable that doesn't make sense. So n is going to be the population. R is just your rate of proportionality. The rate of change is dn dt. All that's good stuff. The population threshold k, that's kind of the newer variable in this sense. And this is actually an example of a logistic differential equation. Which all logistic differential equation is just an addition to a differential equation that adds a limiting factor, essentially. Okay, so I want to break this down like in a graph. All right, so I want to move this down a little bit. Let's look at a graph. So this is going to be the graph of n of t. So n's the population, t obviously is time. And we're going to say we're going to have some k. So let's make it red. So this is going to be our population threshold. So however you found this, some scientists said, hey, listen, if it ever came to the situation where this population of organism grew to this point, resources are not going to be able to be sustained. So like if they get past that point, it's going to be just like a nose dive down, because they're going to run out of resources, they're done. That population's toast. So that's that threshold, and somehow based off of a ton of factors, a scientist could make that estimate of what they think. Just like with people, like I'm sure there's plenty of notes and plenty of people out there who have talked about what is the human population threshold? How many people can this Earth sustain? So there's a couple different I guess things you can notice about this. So let's actually look at put it down here. If n equals 0 at time 0. So if n equals 0 at time 0, All right, so that red dot represents that beginning population. Let's kind of see, the biology word is carrying capacity. Yeah, exactly, Liberty. And we're actually going to talk about that in a second. I'm saying population threshold. We'll talk carrying capacity in like probably 5 minutes. But yeah, you're exactly right. That's the word I'm going to use from here on out, is carrying capacity. Just for this specific example, we're going to talk about this population threshold. So let's say we start 0, 0. So let's say there's no animals at time 0. Using our model, let's see if this makes sense. Okay, if I were to plug in these values of n equals 0, t equals 0, I'm going to end up getting r times 0. Right? And then times, it doesn't even matter what happens in here. It's going to be 0 times anything. So my rate of change will be 0, meaning that if there's no rate of change when I have no population, then it's just going to stay on that axis, right? That models my population growth. So that shows my logistic differential equation works for that situation. The other scenario we could have is if n naught is equal to k. So if our starting value is already our carrying capacity or our population threshold, if it already starts there. So basically I have a dot right here, right? Well, let's look back at our logistic equation. If I were to plug in that n, well, n is k, right? If that's my initial population, those are equal, then I'm going to have k over k, which is 1. 1 minus 1 is 0. So this actually works in our favor. This is what we were looking for. We want to get a model that's going to not let anything cross that asymptote, which this proves that there's no way it can if it starts right there. So that shows you, I thought graphically would be the best way to approach it. This shows you where this equation can come from. The idea is that we have to create something so if we were to hit our carrying capacity, we're not going to have a rate of change. It's never going to exceed that. Because if there was a rate of change, even if it equaled 0.01, that would mean that it would go past the carrying capacity. All right, and we know, again, just as a reminder, right, this is a derivative. This is a derivative. So the derivative equation models the rate of change of the original function. So the rate of change of n. So if I get this to be 0, it means that the rate of change of n was 0. Meaning at whatever point it was at, it's not going to change. It's going to stay at that value. Not entirely realistic. We know like there's a ton of factors that can involve in that, like animals, predators, all that stuff. So, but this is just like, again, it's just a model. It's not something that's going to be an exact way to express situations. Okay, the last case of scenario we have is if n naught is between, I apologize. If n naught is between 0 and k. Obviously, you guys notice, like, I'm only using quadrant 1. It's population. Population, first of all, time is never negative, right? So you have to start at t equals 0. My population doesn't become negative. If it's 0, it's dead. Okay, it's died out. So my last situation, like I said, is if 0 is less than n naught, which is less than k. So what you'll see is if we can pick a bunch of values, it's going to affect how our graph grows. All right, so let's just say that let's say this is n naught. So this is my n naught in between 0 and k. The shape of these curves is going to look something like this. Just make a little dot there. All right, that's going to be the shape of our graphs. Now, I could show you, you guys can see for yourselves, but this graph just comes from just imagining us picking different values of n naught and plugging them in and seeing what happens. Okay, and when we do that, what we see is an initial beginning of our graph has a pretty slow increase in the slope. and then it increased very rapidly. So it goes from concave up to concave down. There's a point of inflection, which you guys will see later is going to be super important to this lesson, is this idea of this point of inflection. That's a very important piece of this puzzle for us. Okay, and then what happens is as it gets closer and closer and closer to K, the rate of change is going to get smaller and smaller and smaller and smaller, which means that it's going to slowly be approaching that asymptote at a slope of 0, which is, again, like I said, that's what we wanted to express. So the idea is that our population starts off somewhere, starts making babies, starts getting a little bit bigger, and then gets bigger exponentially, but then it starts getting to a point where resources become scarce. Things are very difficult to fight for. People or animals or whatever are dying out. They're competing with one another. More predators are introduced. Whatever it may be, there's all these inhibiting factors that will prevent it from crossing that asymptote. This is a much more realistic model of what could happen in the real world. Okay, so that's what we're looking for there. That's kind of an introduction to logistic models. Is there any questions you guys have you'd like to ask? Nope. So I think for spring break, guys, I'm going to assign you to watch the Lorax. The Lorax will be a perfect distinction. And actually, I want you to make a logistic model representing the Lorax. That's going to be our new assignment that I just thought of. That'll keep you busy for a little bit. Actually, it would be kind of fun if there was a way to do that, which it probably is. I could probably think of something. I'm not going to. Don't freak out. I'm not going to give you that assignment. But maybe if we get to a point where it's like, AP test is done, I can be like, that'll be something we can do. Okay. Flipping the page. So I'm going to write the logistic form we're going to use. And this is going to look a little bit more familiar than the one we were just talking about. We just said, nah, we'll just watch it. Yeah, you guys can just watch it. That's fine. Liberty, for spring break, we must speak for the trees. That's what I'm saying, Liberty. See, if you ask the trees, they're very excited about this whole situation because they're like, wow, no one's bothering us. We're just free to do us. No one's chopping us down. People are just leaving us alone. Let's speak for the trees. Maybe the Lorax was the whole thing behind this whole situation. All right, you guys ever think of that? Something to think about. I don't want to start conspiracy theory, but we might have a real life Lorax roaming about. All right, so this is what I want to use, this equation. And like Liberty said, we're going to call A our carrying capacity. So the model we used before, we used this idea of 1 because that entire parentheses that we had before was just basically a way to multiply by a fraction that's less than 1. Because if we multiply by a fraction more than 1, it's never going to be limited, right? If you're multiplying your population by 7, it's just going to keep growing. It's not ever going to stop. So we said 1 just to create that fraction. Now we're going to change things a little bit by doing an actual population and then the carrying capacity. So again, P is the population, K is my constant of proportionality. So this will be the general form we use. I'm going to copy down this problem, guys. This is going to be our first example we do, so go ahead and copy that down as well. Okay, so population P of T of bacteria in a petri dish satisfies the logistic equation written there, where T is in hours and P of 0 equals 700 bacteria, or P naught. So one of the big questions that you'll be asked is what is the carrying capacity? Okay, Liberty, I don't understand why we are using two different terms for carrying capacity, population threshold. How are we differentiating their meanings? Again, so the problem I gave you before, that situation, that I guess equation, you're not going to see. That one's not going to be seen for AP or for Con. That's just another way we can model that situation. They're the exact same thing though. Population threshold and carrying capacity are the exact same thing. The carrying capacity just allows us to do more generic problems rather than like just sticking to just population. We can just call something a carrying capacity. So that's different. I guess that differentiates their meanings. This is going to be the one we're going to use. So the one that you guys just copied down, we're going to stick almost entirely, I think entirely, to that equation. So hopefully that answers your question, Liberty. And just as a reminder, this is going to have the same effect. So you guys think about that little thing we did with the graph before. It's going to be the exact same outcome. If your carrying capacity is 600 and your population gets to 600, this rate of change is going to turn to 0, right? So you're going to have 600 minus 600. So it's going to have the exact same effect. The only difference is now we're just expressing it a different way. All right, so let's look at how we can solve for the carrying capacity. So what we want to do is we want to get in this form. We want to write in the form of Kp times A minus P. Right now we have Kp times something minus P over 8,000. So that 8,000 is kind of messing us up a little bit. So how we're going to do that is what we want to look at is kind of the example I gave before. What did you guys notice when we got to the carrying capacity? What was the derivative equal to? What was the slope of the line, the tangent line there? So if you guys remember that example I went through, as my graph was approaching the carrying capacity, my slope was changing to 0. So my derivative was approaching 0. So we know the carrying capacity occurs when my derivative, or dp dt, is equal to 0. That's a definition of a logistic model. It's approaching a carrying capacity. So when it approaches that carrying capacity, the only way that it stays below it or on top of it is if the slope's 0. So it can't get any bigger. So all we got to do is then say, well, 0 is going to be equal to 2p times 6 minus p divided by 8,000. Okay, so we're just solving this now. So we want to actually solve the situation. The only way this can be true, the only way 0 can equal that, is if either 2p equals 0 or the inside of parentheses equals 0. 0 equals p, that's obvious, and that's kind of like that's always going to be the case. If the population's 0, obviously it's not going to grow. But we don't consider that the carrying capacity. All right? So we ignore that solution. What we want to focus on is inside the parentheses here. So we get p over 8,000 equals 6. So p equals 48,000 bacteria. That's what we call the carrying capacity. So just like that graph I showed you guys before, we started off that we knew 0, that's going to be definitely a limiting factor of population, which makes perfect sense. It has to be. That's not what we call our carrying capacity, though. Our carrying capacity is the most the population can get to without it entirely dying out. And so in this case, we find it's 48,000. Because the idea is we want to figure out what would make this parentheses 0. Because that means the rate of change will be 0, which means that that's hitting our asymptote, our horizontal asymptote. Okay, so I'm just going to stop there. If you guys have any questions, go ahead and ask before I move on. So A does not equal our carrying capacity. No, so A is still our carrying capacity. Yes, exactly, Liberty. This is just rearranging what's inside the parentheses to resemble A minus P. That's exactly what we're doing. There's another way we could do it. The other way would be multiply everything by 8,000 and then divide this by 8,000. So we'd have to change the entire equation. That was the other option you have. I want to stick to just one single way to do it. And I think this is going to be our best option. So yeah, A is always our carrying capacity, except the issue is we have to, in order for it to be our carrying capacity, it has to be in this form. Again, the reason it has to be in this form is because our carrying capacity, once you subtract the population, this has to equal 0. So we have to find a value that makes that true. Now, you guys can see, right, just looking at this, like this work doesn't necessarily have to happen. Okay, I know some of you guys are smart enough, right? We can look at this and just say, well, what does P have to be to make this 0? That's the question at the end of the day. What does P have to be to make this 0? Now it has to be 48,000 because 48,000 divided by 8,000 gives me 6, and 6 minus 6 is 0, right? So we're just trying to find that value of P that would create a derivative of 0. So we have no rate of change anymore. Hopefully that clears it up a little bit. Okay, next big question that you'll get with logistic equations. I'm going to go on the back page. It's going to be question B. And that question is, what is the population size when it is growing the fastest? It meaning the population. Okay, so let's break down what that's saying. It says, what's the population size when it is growing the fastest? So we're saying when the rate of change is the highest. So when is the rate of change the highest? And at that point, what's the population? That's what this question's asking. When it says it is growing the fastest, it's growing the fastest when we have the maximum number for our derivative. And that's the key word there, is that word maximum. So I want you guys to look at what we were given. So we were given this derivative. This was given to us in the problem. 2p times 6 minus p over 8,000. If I were to distribute that 2p, I'm going to get 12p minus 2p squared divided by 8,000. You guys can see this is a quadratic equation. All right, my logistic growth is represented, or my logistic growth rate, I should say, is represented by a quadratic equation, which actually works pretty well for us. Because we want to know, when is this equation right here, when is it at its highest? We want to know that because where this equation is at its highest is our maximum point, which means it's the highest rate of change. So we want to do that. And we have a special way to do that. So I'm just going to put like a little bullet point here. So if we're actually finding a maximum point on a quadratic graph, this is like way, way back, throwback to like algebra, But it's a good reminder. If we're finding a maximum point, remember that quadratic equations or graphs of quadratics are symmetrical. They're perfectly symmetrical. So you can find where your max value occurs or your min value, your vertex. You can find where a vertex occurs on a quadratic. It's halfway between the x-intercepts. So if we're looking for at what value, at what time is this going to be at its maximum point, we could just first have to find the zeros. All right, and then after you find the zeros, halfway in between them is going to give you your max point. Okay, so let's look at let's actually do that. So we're going to say 0 is equal to, well, we already did the work for it, right? So 0 is equal to, in this case, 2p, again, times 6 minus p over 8,000. So we already did the work for that. And what we found is that p equals 0 and p equals 48,000. I'm just now realizing before I was putting an or. I don't know why I was doing that. Like these should be ands. I guess if we're looking for a carrying capacity, it's actually just one or the other. But when we're solving a quadratic, it's an and. Back to here, though. All right, so we already did the work for that. We found that. So in order to find the midway point or the halfway point, or our maximum, that's going to be 24,000. So 24,000 is the halfway point between 0 and 48,000. Okay, so not too much work actually. And if you guys notice, we don't even have to do anything extra because we always know our zeros are occurring at 0 and it's occurring at our carrying capacity. Okay. So I'll stop there. Let me know if you guys have any questions on that. What's really nice is these two questions will go hand in hand, meaning once you get the carrying capacity, you can find what the maximum population is at the maximum rate of change pretty easily. Again, if you have any questions, let me know. If you're good, let me know you're good. I think I'm good. Okay. All good. Okay. So let me try. We have 8 minutes. Let me try to fly through one more problem. All right. So this is going to be 2. So we have dy dt is equal to 0.2y times 1000 minus y. I'm doing this example because I want you guys to understand it doesn't have to be always in terms of p. It's not always in terms of population. I mean, it usually is in terms of population, but the variables can change. So just because the variables change doesn't mean like how we're analyzing it's any different. We're just switching out p with y in this case. This is going to be population growth. I'm just trying to be quick, so I'm not writing out like a formal problem. So the question is, what are all the values of y for which the population is increasing at a decreasing rate? That's the question. So we're given this logistic model that represents population growth. What are all the values of y for which the population is increasing at a decreasing rate? So we want the population still to be going up. Okay, so it's not declining in any way. It's just the rate of change is going down. All right, and we can think about like our original graph, like the graph we did when I started class. And we can kind of think about that and we can picture when this might occur, which is going to be right around that inflection point in our graph, but we got to get an exact value. So remember, dy dt is a parabola with a maximum point. Which means that population is positive, but rate is decreasing after the maximum point. So let me just show you kind of like as a graph what we're thinking. If this is the graph of dy dt, it's going to look something like this. So this is the graph of the rate of change of y with respect to t. All right, so this is going to be the highest rate of change. Notice that the rate of change is always positive. It's always positively changing. The rate's always positive. So we know that it's always going to be the population, because the question said, what are the values for y for which the population is increasing? Well, every value of y, the population is increasing. The only time it stops increasing is when we hit our carrying capacity. So it's always doing that. So I'm not really concerned about that. What I'm more concerned about is when is it a decreasing rate? Well, if dy dt represents the rate of change, notice where is this decreasing? Where is the rate decreasing? Well, from 0 up until that point, it's definitely increasing. The rate of change is getting higher and higher. Once we hit that maximum point, everything after, so everything in the blue here, that is where my rate of change is decreasing. Okay, and I just made that really obnoxious just so you can see what I'm saying. So at the end of the day, what this question is really asking me is, all right, where's my maximum point? Any point after that and my carrying capacity, those are going to be the values of y for which the population is increasing. So that brings us to finding what dy dt is equal to 0. Meaning 0 equals 0.2y times 1,000 minus y. So 0 equals y, and 0 equals, y equals 1,000. So my y equals 1,000 is my carrying capacity. And my max occurs at y equals 500. Because 500 is halfway between 0 and 1,000. So that's on this graph, that point, that red dot up there is going to be at y equals 500. So my final answer is going to be 500 is less than y, which is less than 1,000. Between that max point and my carrying capacity is where I'm going to be having an increase in population, but a decrease in the rate of change. Okay, that's the really big idea of this logistic models, guys, is we want to focus on carrying capacity is a huge important part, and then understanding the graph of the derivative. It's always going to be a parabola, whether it's a parabola going it's upside down or right side up. Generally, we'll see one that has a maximum point. So we just have to understand what that information is giving us. Okay. So that marks today. Again, guys, we don't have class tomorrow. I will be here from 1 to 2 to answer any questions in my office hour if you guys have any. If not, I hope you have a great rest of your day. I'll see you Wednesday. There is a Khan Academy tonight. I think I already assigned it to you guys, logistic model word problems. So you guys can go ahead and get started on that today. And hope you enjoy the rest of your day. BC. I will. Thank you, Rachel. Thank you, Liberty. See you, Hunter. Take care. Welcome, AB students. We'll get started in about 5 minutes, probably. If you guys are funneling in, you guys can go ahead and open up the calendar. We got some stuff to discuss. Good morning, good morning, good morning. What's up, guys? Welcome to week 3, Jasmine. Technically, this is supposed to be the last week of this. It's supposed to be. I think most people are very pessimistic about that, and I am as well. But I guess crazier things have happened, right? crazier things have happened. Morning, Peyton. How's everyone's weekend? Let me hear. You guys have good weekends? We doing all right? We happy to get started with the week? Are we upset? Good morning, Alexis. Morning, Brandon. If you guys are all ready for class, go ahead and hit that like. You know how it is. Just would really mean a lot to me. Helps me keep the lights on, keep the air flowing in my apartment. Buying food, your guys' likes go a long way. So pretty boring, but Sunday was nice. It's really nice outside Sunday. It was windy, but it was really nice. It was nice just being outside. A little boring, yeah. I think probably everyone has that consensus of it being a little boring. There's not a lot for us to do. It's kind of a situation. I got to I guess it wasn't FaceTime, it was like Zoom. So a bunch of my friends, we got together and we did like a Zoom meeting, which was pretty fun. You gotta do what you gotta do to stay I guess involved. Keep your connections. I've been like calling people all the time and stuff. Just out of pure boredom. So again, guys, if you're just tuning in, go ahead and go to the calendar so we can talk about that. Hey, morning, Josh. All right. I think we can get started here. Let me log in real quick, though. Okay. So, calendar-wise, let's take a look at this. So, we talked about this last week. We mentioned this. So, I kind of said to you guys, like, I'm not sure how we're going to handle it moving forward. And I just looked at everything, did some thinking. And I think what we're going to do is try to stick to, I don't really think I have too much of a choice, but we're going to stick to our stream going 3 days a week. So you guys will see that I don't have Tuesday and Thursday. So again, I mentioned this, and I think you'll hear this from other teachers, but Monday and Wednesday are considered math days. So math and science. So you're dedicating your entire day to your math and science classes. Which means what is supposed to happen is we're supposed to only focus on those subjects those days. I will be giving you assignments that are expected to be completed on those days. So my expectation is, I'm going to do the notes as usual. I'll introduce these topics. We'll go over stuff. And then you guys will have this assignment. You're supposed to be doing it on a Monday, right? Again, it's supposed to be dedicated strictly only to math and science. So that's what we're going to do. That's what administration wants us to do, so that's what we're going to do. So that means Monday, Wednesday is going to be math lessons. Now, you guys are done with Calculus AB after this week. So Monday and Wednesday are going to be the last two topics we need to address. I don't know about Wednesday if we're going to pick up it at all after break. So we'll find out with that. But as you guys know, next week is spring break. So we don't have anything next week. No work. Well, I shouldn't say that. I should say no streams whatsoever. Now, you'll notice that today we're going to do 10.2 notes, and we're probably going to review College Board. I know we did most of it, but if you guys had any questions on homework over the weekend, I guess we can go over one of those too. And we're going to do, you have a homework assignment. That homework assignment, I believe, I can double check real quick, but I don't know if I might have made it due Friday. Because I'm not really that concerned. I mean, I know if you guys want to do it and get immediate feedback on it, you'll just get it done by Wednesday and then ask me questions on it. But for some people who need that week or really like have a lot going on or whatever, like I want to keep it open so I don't have to keep reopening it. Because that's always a pain when someone, like a bunch of people email me, hey, can you reopen it? Can you reopen it? So I might as well just keep it open. Let me double check what day so I can be exact. But yeah, we're going to do that. That's going to be tonight's homework, I guess, homework. It shouldn't take, so the idea is also we're not supposed to be giving you assignments that take more than 30 minutes. I'm not going to guarantee I can keep you to that, but I'm going to try my best not to like do anything too crazy. The whole idea, right, is just trying to keep you guys, ease your minds a little bit, like make sure you're not panicking and, going insane. So I think that's the goal of it all. Yeah, so you guys have till Friday, actually, for tonight's homework. So this homework I made, this isn't due till Friday. So just keep that in mind. But regardless, like my recommendation is if we're going to be doing this format, and I got to imagine every teacher's doing this format, maybe a couple, because you guys are AP kids, maybe some AP teachers might not be. Because I think I mentioned to you guys last week that there was talks that maybe things would change a little bit. The more I thought about it, I don't think we need to do every day. I think it's actually going to be kind of beneficial to give you an assignment, give you 2 days to work on it, and then review it then the Wednesday. And then 2 days to work on it and review it Friday. So that's kind of, I actually think this is going to be conducive. For the rest of the year anyways, we're going to be doing review. So that means that I'm not going to be teaching you anything new anyways. So all we're going to be doing is assignments from here on out anyways. So I think I'm just going to be doing that, giving you a little bit beefier assignments to work on, and then you'll have 2 days to do them. So that's the plan. Again, the idea is you're not supposed to be doing them on working on it on Tuesday, but I don't really see if you don't feel like you're going insane, you want to save it for a Tuesday or Thursday, go ahead. So that's gonna be a little bit changed, which means tomorrow and Thursday we're not gonna be doing. I won't be on, okay, at all. So that includes I'm not going to be doing an office hour because I don't see a point of doing an office hour if I'm told you're not supposed to be working on math at all. So I guess technically I'm not supposed to be here to answer any questions. Now, with that being said, I will be. So I'll be on the computer from, whenever, like all day. So if you guys have questions, just email me. I'll definitely answer you. I'll get back to you. I'll find a way to give you the information. But if not, here's what you guys got to understand. If you're working on something Tuesday, again, I think Monday, the best thing to do, I think, is to dedicate your Mondays to math and science. So I really think it'd be beneficial if you guys dedicate your days to those, which means try to be very disciplined. Meaning after my stream is done, work on the homework. Just start it now. Try to get it done now. That's my recommendation to you guys. Don't just put it off till Tuesday and then or Wednesday and figure it out. I think that'll be the best case scenario. If teachers are going to be nice enough to give you these dedicated times and relieve the stress for you, don't procrastinate. Take advantage of the fact that you're getting specific days for specific subjects. That's my recommendation. So just understand that Tuesday, if you're doing an assignment, you have a question, email me and I'll answer. But even if you don't have a question, I can answer it Wednesday. So on my stream Wednesday, I'll take time to answer you guys' questions from whatever Monday's assignment was. So don't panic if there's a question you can't answer and you're oh God, I need to get it done. I'll be available Wednesday to talk about it. So just don't stress yourself out. Just say, all right, you know what? I'll worry about it on the day of math, which is Monday and Wednesday. Okay. Friday. Friday is going to be the idea is every Friday, all the teachers, it's going to be thought of as like a recap day. So there's no specific subject on Friday. It's every subject, but it's just a day to review. So like the way I'm going to treat it is I'm going to just whatever we did Monday and Wednesday, Friday will be used to review all that. Okay, so I'm not supposed to give you guys assignments on Friday, from what I understand. I'll get more information. We have a meeting today, so I'll get more information from our meeting. But from what I understand right now, Friday you're not supposed to give assignments over the weekend. That's my understanding. That might change because, like I said before, I gotta get you guys ready for AP test. I gotta do whatever I can to get you ready. So if that means I have to assign you something over the weekend, you guys can suck it up. I think it'll be all right. So we'll figure that out, future us. But as of right now, it's just going to be an office hour, basically. If you guys want to hop in and ask any questions for Monday and Wednesday, absolutely do it. If you don't, then don't. All right, take your time, do another class, work on another class, or just, your week's over. You're good. Now, big thing too, I know this is probably a lot of people are thinking about, is over spring break. What are we going to be doing in this class? I won't be doing any streaming at all. Everything, any topic we do will be review, and it'll be reviewed when we get back from break. So not next week, Monday, but the following Monday, we'll review whatever we do. You can see on my calendar I put TBD because I don't know what I'm doing yet. It's all going to be based off of this week. I'm supposed to find out what's going on with AP. So they're supposed to give us like an exact answer of what the AB test is going to look like. From my understanding, it's this. You guys will have 45 minutes to do a free response question or multiple free response questions. And that's it. Your entire AP test your entire year of AP calculus is going to boil down to a 45-minute test. Is what my understanding is. Which is good, I guess, in a sense, because, it's going to be shorter, first of all. You don't have to worry about multiple choice. It's just free response questions. I don't know. Maybe that's good to you. Like, personally, I don't like that at all. Like, if I was in your guys' situations, that'd probably be like, I would hate that. Just because, first, you put all this time, obviously, into it. But also, your room for error is going to be very, very slim. Like, your margin for error. So when they grade it, if they're only grading, if you have 45 minutes to do a free response question, you have maybe, 2 or 3 free response questions. You don't have very much room for error there. So we gotta be careful with that. With 4 questions, yeah, that's the thing that's crazy, Jasmine, is like that, and that's what I don't understand, because I remember reading that they were gonna give just an FRQ for all the classes. That's okay, Drake. I kind of figured. I was thinking to myself, like, they gotta do this like every single class. They gotta mess this up. Like, calculus has to be a little different, and then it doesn't look like it's any different. It looks like it's the same. I don't know yet, though. Like, don't quote me on that. They're supposed to release it by Friday. But if it is just free response questions, yeah, and you have like 4 questions, those are pretty high stakes questions. All right, which in my opinion is kind of annoying and unfair. But I got to imagine they understand that, and because of that, they're probably going to make it watered down. Again, this is just all my prediction. It's nothing like I can't confirm any of it. It's just this is such a weird situation. I doubt they're going to hold this against you, which means I think they're going to give you every opportunity to do really well in it, would be my prediction. The only people who aren't going to do well, and I'm assuming, would be the people who just have no clue at all what's going on. Like, don't even know how to take a derivative kind of situation. That's my prediction. Again, I'm just spitballing here. I want you guys know how my mind's working right now through it. With that all being said, Friday, that TBD will change. What I'll probably do is I'll give you the assignment over Google Classroom. I'll probably just set up in the stream. I'll probably just make a post that's saying like, hey guys, here's your homework over the break. And it's not going to be anything crazy. I'm not going to ask you to do anything insane. It's going to be maybe like 3 free response questions or 4, something like that. Okay. So just keep that in mind. I want to get you guys prepared for that. All right, let me get a drink of water. And let's talk about the College Board. So let me go to here what we're going to be doing today. Did you guys have any questions on the College Board? I'll probably do like maybe one. I can't do too many. It's due at 3:30, so make sure if you didn't get it done or you haven't submitted it, just make sure to go submit it at the very least, okay? So even if you don't think you're going to get it done and you've done some of it, submit what you have, and I'll grade what you have at the very least. I mean, obviously, try your best to get it done by 3:30, but if you guys have any questions on that, I know I went through most of them, so. Oh, it's raining. I'm a big fan of rain. I don't know about you guys. I love rain. I mean, I guess it's not always great. Sometimes it's really annoying. But if I'm not doing anything, if I'm just relaxing, rain's the best. It's so relaxing and calm. It's fantastic. That was Mr. Harris's rant on rain. Thank you. I appreciate you guys for listening. Questions on the AP work. Apparently Saturday morning at 5:08 there was lightning strike so bright I was seen from Northern Ohio all the way to Tennessee. Jeez. And you know what's funny, Drake, is I don't know. Okay, I didn't hear the one at 5:08, but I gotta be honest. I was up really early on Saturday. Well, I was sorry. Let me rephrase that. I was up really late on Saturday. Like I stayed up really late, and like it was like really like it was probably like 2 in the morning or 3 in the morning or something, and I was just chilling and I heard lightning and thunder, and it was like the loudest lightning strike I ever heard. It was crazy. I believe it. It was like very very powerful lightning and thunder, from what I could tell. Okay, I'm assuming we're good. I'm gonna ask just because maybe I don't know. I saw some crazy lightning. I was up at like 5. Yeah, seriously, it was loud. Josh says alien. Oh, was it an alien? Okay. So that's an interesting take on that, Josh. I tend to see. I believe in aliens. I just don't believe in like the idea of what we think of as an alien. I don't believe in that. I believe that there are other life forms, though. What they look like, where they're at, who knows? But there's got to be some organisms somewhere. Then again, though, that'd just be assuming I believe with everything. I believe everything scientists tell you, which I don't know, I don't ever see any proof, so I don't know. Maybe the universe isn't as big as we think it is. Maybe we're getting fooled. We're getting duped. Okay, so I'm not getting any feedback on that College Board, so we're good. All right, which means that we are going to start on today's notes. Woohoo! Yeah, notes. Yeah, Mr. Harris, let's do some notes. Woo! Thank you guys for the round of applause and the energy today. Really appreciate it. Today we're going to be doing 10.2 slope fields. So that's what you can title your notes. You might see the word direction fields. I think that's dumb, so I'm going to call them slope fields. But no, I might refer to them as other fields too. Josh is speaking in code now. He just put a plus sign. So I'm a little bit worried. I don't know what the plus means. It might be like some alien code he's trying to speak with me. I don't know. But Josh, I agree. You're right. Plus. Plus is correct. All right, so guys, that's going to be your title. I want you to turn to page 608. Josh said, don't worry about it. All right, Josh. I won't worry about it. You keep doing you. 608, people. Mr. Harris, what page are we going to? Read the chat. Okay, Brandon. You're going to speak in Morse code, and I guess it's not Morse code, it's binary code. You're going to speak in binary to me? Guess what? I know binary. Joke's on you. Mr. Harris, can you fail me for the quarter? Yeah, Brandon, I could do that for you. Thank you for asking politely in binary. Would love to fail you for the quarter. I can do that. Get right on that. All right, guys, 10.2, direction field. They're going to call them direction fields, but also known as a slope field. Okay, so this is one of my favorite topics in calculus. I really enjoy it. We're not going to spend much time on it. We're only going to spend a day on it, really, and we'll see some review as we review. But I really like this topic. I think it's kind of interesting. It's like a cool way to look at graphs, and this is going to be like brand new for you guys because you've never seen a graph like this. So these are called direction fields. I'm going to refer to it like as a graph because it's on a graph. It's on a set of axes, but it's called a field. Okay, and let's talk about what this is. So you guys can see on this page, I'm going to start reading. Try to follow along as I go. So it says, ultimately, it's impossible to solve most differential equations in the sense of obtaining an explicit formula for the solution. So you guys have seen we have gotten some explicit formulas based off of initial conditions. Like we've accomplished that task. But it's it doesn't happen very often. It's very difficult to do. All right, so in this section, we show that despite the absence of an explicit solution, we can still learn a lot about the solution through a graphical approach, which we call direction fields, or a numerical approach called Euler's method, which we won't learn. That's just BC. So for as long as we've been in math, okay, as long as we've been in geometry and algebra, we've always used graphs as a way to approximate things. You can look at a graph and guess an area. You can look at a graph and guess a length. You can look at a graph and understand or assume a slope. You can assume point values. Like there's all these assumptions that can be made from graphs, which is why we use graphs. It tells us a lot. It gives us a lot of information. It's the same idea. That's what we're going to be doing. We're going to be creating these direction fields or slope fields as a way for us to understand the behavior of our differential equations. All right, so I'm going to move on to this next section. It says, suppose we were asked to sketch the graph of the solution of the initial value problem, y prime equals x plus y, and y of 0 equals 1. So that's going to be our derivative, right? Y prime. We don't know a formula for the solution. So how can we possibly sketch a graph? Right? We don't know the solution, so how do we sketch the graph of the solution? That's the question we want to figure out. That's the goal of the direction field. So these direction fields are going to be the solution sets. They're going to graph the solutions. But we don't actually have the solution, so how do we do it? Okay, so let's think about what the differential equation means. Let's go back to the roots. What is a differential equation? So this equation, y prime equals x plus y, tells us that the slope at any point, xy, on the graph, which is called the solution curve, is equal to the sum of the x and y coordinates of the point. So that's what this is breaking down. We started with derivatives. The whole point of a derivative was we were telling you the slope at a point. That was all we were talking about with the derivative. From when I first introduced derivatives to you, that was always the underlying idea. Is that derivatives giving you the slope of the tangent line at a point. Okay, so your solution is going to be the slope at a specific point. And to find that, you add the x and the y value. So by adding the x and the y value, this specific coordinate point, whether it's 1, 2, 3, 4, 0, 1, whatever it may be, and you plug that in, that gives us the slope at that point. Which is really, that idea is the whole premise of these slope fields. In particular, because the curve passes through the point 0, 1, its slope there must be 0 plus 1 equals 1. So at the point 0, 1 on the original graph, the slope is 1. Because we have an equation that tells us the slope, we just have to plug in the parts. So a small portion of the solution curve near the point 0, 1 looks like the short line segment through 0, 1 with a slope of 1. It says see figure 2. So guys, look at this figure 2 over here, where my finger's at. This shows you how we can represent in our slope fields, how we represent this solution. So the beginning of the solution curve through 0, 1, we don't know what's happening at 1, 1 yet. We don't know what's happening at negative 1, 1, nothing around there. We do know at this point 0, 1, the slope is going to be 1. So to draw that, we just draw like a tiny little dash. Okay, and it's really hard to see, but this dash is supposed to have a slope of 1. So if I were to take this, and if I were to stretch it out, stretch that line up, the slope of that line would be 1. That's the idea. So a slope field is going to take a bunch of different points, like a ton of different points, and just draw these little dashes that represents the slope at those points. Okay? So as a guide, so back into this paragraph, as a guide to sketching the rest of the curve, let's draw short line segments at a number of points with slope x plus y. The result is called a direction field or a slope field. And it shows in figure 3. So for instance, line segment at the point 1, 2 is a slope of 1 plus 2 equals 3. The direction field allows us to visualize the general shape of the solution curves by indicating the direction in which the curves proceed at each point. Okay, really, really important, that last sentence there. Right there. This slope field, this direction field, okay, the whole point of it is it's going to give us a general understanding of what the solution curve looks like. All right, so they went through and they found all those points. So on this graph here, on figure 3, they actually went through and graphed every single point here and the slopes at every single point. So it approximated the slopes at every single point. So they did the hard work for us. You can see, guys, based off of the way these little dashes are, you can draw a sketch of what the graph apparently looks like. So you can see, like up here at the top, it looks like it's some sloping down. So you're going downwards along, and you can see there's like an asymptote, right? Looks like there's like a diagonal asymptote right there. And this graph is going down, and then they start escalating really quickly. So like all of the points, or all the dashes over here, are very steep. So that means that your graph is going whoop, flying up. And you can see in the red there in figure 4 is the solution that they sketch. So they're just kind of following the path of these blue marks with their red line. That's what we call a solution curve. Okay, very, very important idea. So AP, a lot of questions will ask you questions based on the understanding that the slope field, the point of the slope field, is it's going to give you a solution curve. Or at least give you, be able to see, eyeball what a solution curve would look like. Okay, that's the general update of what a slope field is. Okay, moving on to 609. So the top is 609. Whoops. Now we can sketch the solution curve through the point 0, 1 by following the direction field as in figure 4. Notice that we have drawn the curve so it is parallel to nearby line segments. In general, suppose we have a first order differential equation of y prime equals capital F of xy, where f of xy is some expression in x and y. The differential equation says that the slope of a solution curve at point xy on the curve f of xy, if we draw short line segments with slope of f of xy at several points xy, the result is called a direction field or slope field. So what separates a direction field and a slope field from a solution curve is that really weird, distinct graph like I showed you guys on the page before, where it's just like a bunch of tiny little lines. They're unmistakable. You can't mistake them. Okay, it's very obvious what these slope fields look like. These line segments indicate the direction in which the solution curve is heading, so the direction field helps us visualize the general shape of these curves. Okay, and that's all I want to do in the book. So you guys can close your book and get back to your notes. There's really not much more to it. The only thing left to do really is just practice with these. So the basics of slope fields I just told you. Just another way to express solutions to differential equations. We just got to get practice in doing that. Okay, so here's your first example. Consider dy dx is equal to y minus 1 over x. We're going to sketch a slope field at the 9 points below. Oh boy. Whatever. Okay, so I want you guys to draw this with me. So draw this graph with me. So guys, just type in the chat when you're done with drawing writing the question, drawing that picture. Because I'm gonna have to move down a little bit on my paper. So I just need to know when you guys are done so I can move the screen down. Okay, cool. Thank you guys. All right, so I'm going to scroll down a little bit, and I want you guys to write this as well. So this is going to be a method. Now, you don't always have to do this, but I think, like in my opinion, this is a really good way to organize it. So here's what we're doing. Okay, we're finding the slopes at 9 different points, and those 9 points are as follows. Again, this is just because we're first learning this. This is something that we're going to want to write down now just to keep our work organized. There's going to come a point where you're not going to need to. So I'm going to write down here. Just remember dy dx is equal to y minus 1 over x. Okay, so now the question is, how do we get these little dashes? All right, I showed you a little bit. It's very, very simple. To get all the dashes, all we do is plug in these points into our equation. So this is let's just start here, and then we'll decide what our answers are giving us. So at 1, 0, what is dy dx? Well, if I plug in 1, 0, I get 0 minus 1 is negative 1. Negative 1 divided by 1 is negative 1. So at 1, 0, dy dx is negative 1. At 1, 1, you plug in 1, you get 1 minus 1 is 0. So at 1, 1, you get 0. At 1, 2, you plug in 2, you get 2 minus 1 is 1. 1 divided by 1 is 1. So you get negative 1, 0, and 1. 0 minus 1 is negative 1, divided by 2 is negative 1/2. 1 minus 1 is 0, so at 2, 1 is 0. Okay, and at 2, 2, you get 2 minus 1 is 1. 1 divided by 2 is 1/2. Okay, maybe you guys are seeing a little bit of a trend here. At 3, 0, 0 minus 1 is negative 1 over 3 is negative 1/3. At 3, 1, 1 minus 1 is 0. So that fraction is going to be 0 no matter what. And at 3, 2, you get 2 minus 1 is 1, and then divided by 3. Okay, so those are all of your different answers. So at every single point, there's your solution to the differential equation. Now the question is, how do we make a slope field out of this? So remember, everything you see in the red are slopes. Those are all equal to dy dx. dy dx is the slope of a line, or the slope of a tangent line at a point. So what we're doing is we're just going to recreate all of those slopes at every single point, as if we were to draw like our own mini tangent line at each point. That's what we're doing. We're just drawing like mini tangent lines at each point without actually knowing what the line looks like. Okay, so let's start at 1, 0. My slope is negative 1. So that means that my graph, or my little dash, is going to look something like this. It's not going to be perfect, guys. Okay, I understand that. It's not going to be perfect. But the idea is that if I were to, I'd go down 1 to the right 1. That would give me the slope of that line. Okay, the slope at 1, 1 is 0. So this line is just going to be a slope of 0. So it's a horizontal line. And since we're on this page, right, 2, 1 is also 0, and 3, 1 is also 0. So I can I can draw the slope field for all those points because they're all 0. So you can think of it as like I have like an asymptote at 1 basically. Okay, 1, 2, I have a positive slope of positive 1. So at 1, 2, 1, 2, I have a slope of positive 1. So I should be going up 1 to the right 1. At 2, 0, I have a slope of negative 1/2. So I'm going to still be, it's going to be a very similar line to the one I had at 1, 0, except it was hard. I tried my best. It's going to be a little less steep. So it's going to be a little bit more horizontal, right? Because you're going down 1 and to the right 2. So if you go down 1 and to the right 2, that graph is going to be closer to horizontal. Two, 2 would be up 1 over 2. So again, it's going to be a little bit less vertical. So it's going to be less steep. So something like that it's going to look like. At 3, 0, it's negative 1/3. So now this is going to be like basically almost horizontal. It's still going to have a negative slope, so it's still going to be going like down and then over. And then same idea for at 3, 2, it's positive 1/3. Again, it's going to be like almost horizontal. All right, and that's your slope field. That's it. Okay, so that's the idea of if we're creating slope fields. We're using this idea of the differential equation. It gives us a bunch of different solutions. Okay, because we can get a solution at any point. The question is, what does the curve look like? It's going to be a little hard just based off the points. Like, for example, if this was an AP question, they wouldn't ask you to draw the solution curve or sketch the solution curve. If they did, they would have to give you a little bit more details. I don't really know what's going on over here. It'd be really valuable to me to be able to draw my solution curve, what's happening on the axis. I could find that out pretty quickly. But the issue is you're going to have x is 0 here, so like you can't get any points. Because if x is 0, this is going to be undefined. Your derivative is undefined. So like I can't really even get any information on this. But what you can see for sure is that it looks like as x is getting bigger, my slopes are definitely getting closer to 0. All right, so my behavior, my graph is going to be, it's going to be approaching kind of like an asymptote up here and at 0. That would be the idea. Okay, any questions you guys have in the chat? No, Brian, actually there isn't. I know, it seems like there should be, but this isn't a catch at all. There's nothing actually more complicated with this. It gets a little bit more complicated when we have to start analyzing graphs as a whole. So there's a couple questions that can be kind of worded funny, and it makes you think a little bit harder. But in terms of actually sketching the graphs, no, it's as easy as this. Okay, so no other questions, it doesn't look like. I'll give it one more minute. Okay. So let's do, I'm going to give you guys a practice one. So I'll let you guys try on your own. All right, guys, this is going to be your problem. I'll let you guys work on this on your own. I'm sorry, it's all crooked. It's kind of hard. The way like the angle of me writing is like I'm not right behind it, so I'm writing it like from the side. So a lot of my stuff kind of just turns crooked, but I think you get the gist. So the points are -1, 1, 2, 3, 0, 1, 2, 3, 1, 1, 2, 3. Those are the 12 points. No decimals or anything. So I want you guys to draw the slope field using those 12 points. All right, guys. Looks like people are finishing up. Maybe 1 more minute, 2 more minutes. Okay, about 1 more minute, guys. Finish up. Okay, so let's take a look here. So again, the idea is I'm not going to write down every single point. I'm going to do it in my head. You guys might have written down. That's absolutely fine. Just try to follow along as I go through in my head. -1, 0. Let's start there. So at -1, 0, my y is 0. So 0 minus 1 is -1. -1 times -1 is +1 over 4. So 1/4. So it's going to be a very low sloped line. Probably even more so than that, but something around there. If you guys got that, you're good. Let's try -1, +1. So I'm going to have y will be 1 minus 1 is 0. So I'm going to have a horizontal line there. And I'm just going to go ahead and fill this out. If y is 1 at any point, you're always going to have that horizontal line. Okay, because it's always going to turn that parentheses into 0. 0 times anything will always be 0. So every single time y is 1, we're going to have that horizontal line. I'll get that out of the way. Okay, let's try -1, 2. So 2 minus 1 is 1. 1 times -1 is -1. So my slope is going to be a -1/4 here. So something like that, pretty close to horizontal, but not quite horizontal. -1, 3. I'm going to have 3 minus 1 is 2. 2 times -1 is -2. Over 4 is -1/2. So I'm going to still have a line. It's just going to be a little bit steeper. So just a little bit steeper of a line going in the negative direction. Okay, so anything along those lines you guys had, you're in good shape. Okay, now let's do the easy section. 0, 0. Well, if x is 0, because by the way, x is 0 at every single one of those red points, it's always going to turn this fraction into 0. So this one's kind of nice, right? Those are all just horizontal lines on the entire y-axis. Again, reason being is because when x is 0, that fraction is going to be 0 times who cares? It's always going to turn into 0. All right, making good progress. Next, I have 1, 0. So 0 minus 1 is -1. -1 times 1 is -1. Over 4 is -1/4. So it's going to be -1/4, which means almost horizontal line there. 1, 2. I'm going to have 2 minus 1 is 1. 1 times 1 is 1. So I'm going to have +1/4. So an almost horizontal line there as well. And then 1, 3. 3 minus 1 is 2. 2 times 1 is 2. 2/4 is same thing as 1/2. A little less horizontal of a line. Again, not going to be perfect. Not meant to be perfect. Just have to have like a decent estimate. So you guys go ahead and be honest. I'm just curious. Did anyone get this completely right? 100% right? Go ahead in the chat. Let me know. Did anyone get every single one of those points correct? Nice. All right, so 2 people definitely. Yes, yes, yes. Okay, cool. What do you guys? All right. So that's drawing slope fields. Now, obviously, it's not always this easy. Big idea is a lot of times you'll be given slope fields. So instead of drawing them, you're be provided a slope field, which is more likely on the online AP test you're going to take. It's more likely that you're being given the slope field. So I assigned you guys a College Board assignment. I want you guys to go to that. It's 8 questions. It'll be due, like I said, it's due Friday, but I would like you to have it done Wednesday so we can talk about it, or at least have questions on it by Wednesday. So go ahead and open that up, guys, and I'll actually put it up on my screen real quick. Let me switch over to this camera so you can see my screen. Okay. So this is going to be some of the questions like it's going to be asking you. So it says like which of the following could be a slope field for the differential equation x squared plus y? Which one could be the following? So what we're doing, instead of them saying draw it, they're giving you the drawings. You just have to decide which one of these makes sense. So what I want you guys to do, here's like the strategy I want you to take, or I recommend taking. Do the very, very similar process that we did before. Okay, like as if you were to draw it yourself. What you want to look for is look for the big differences in between these graphs. So every graph has some differences. Look at the different quadrants, like where is there big differences between graphs? For example, like real simply, look at A. Look at quadrant 1. So right up here, look at this quadrant. Every single one of these slopes is positive, right? It's like up 1 over 1 or something like that. I don't know what the value is, but it's positive. Every slope's positive. Let's look at B. What do you guys notice about the slopes of B? They're all negative. Look at all these lines. All these lines up here, they're all negative sloped. So if I can determine in quadrant 1 what's going on in this equation, I can eliminate A or B right off the bat. So let's do that actually. Let's pick the point 1, 1. So 1, 1. I'm looking for the slope to be about 1. Something along there. Well, 1 squared is 1, plus 1 is 2. So that makes sense. Positive 2. That's pretty accurate, I'd say. What about B? What does B have at 1, 1? Negative. That's wrong. So right off the bat, using that method, I can eliminate B. Because quadrant 1 has positive slopes. C, potentially. C could be an answer. D, potentially. Okay? So that's the idea. That's what I want you guys to do. And there's like 3 different questions that are like that. So that's the thought process I want you to take. So I think 1, 2, and 3 are all that. Yeah, 1, 2, and 3 are all very similar. 4 is very similar too. The difference between 4 though is it's just saying like here's the graph. They're going opposite. So 4 is saying the opposite. It's like here's the graph. Which of these equations match? So you'll just pick points. Like let's say you don't do a very good job. Like I don't know, like negative 1, 1. So somewhere around here. Maybe that's going to be the point you pick and figure out what's going on there. Just see, like, what does it look like? Does it match? Will it make sense when I plug it in? So you'll just be taking values from the graph, plug them in. And I think that's 4, 5, and 6 are all like that. Yep. 7 and 8, I'm going to let you guys mess around with. It's going to take a little bit more thinking involved. Okay. All right, so that is today's lesson, guys. Thanks for participating. Thank you for being here. Hopefully this is all right. Your homework, like I said, is the College Board. Please feel free to do Khan Academy. If you guys are still confused with this or you would like even extra practice or your College Board proves difficult, do some Khan Academy. I didn't assign it, but go on there, look at the video, do some practice problems, and I think that'll really help you. The main thing with this is going to take some repetition. Which when we review some material, we'll go over some more. But yeah, that was class today. So guys, thank you. I'll be here from 1 to 2. So any questions, if you want to stop in the office hours, if you're working on the College Board the next couple hours, please feel free to stop by, ask any questions you have, and go from there. So thank you. Have a good rest of your day. Actually, have a fantastic rest of your day. Not just good, make it great. Thank you, Haber. Thank you, Josh. You guys have fantastic days. And anyway, as you guys know, I'll see you Wednesday, so I won't be on tomorrow. We'll see you Wednesday. If you guys are in Algebra 2, hello, hello. Hope everyone's doing good. Let me hear how you guys are doing if you're in Algebra 2. How was your weekend? Is it good? Everything go well for you? Good, Haley. Good to hear. Tanis, I'll talk about that once I get more people in here. Probably like 11:05. I'll start talking. Sierra said, "Great weekend. Awesome. Good to hear." That was all right. It was relaxing. Got to talk to some friends over Zoom, which was funny. It's still not great, not like ideal, but I'm battling through. Molly, yeah, that's kind of where I'm at too, Molly. I'll find any excuse to leave, but I just don't want to be around people when I leave. So it's kind of it's a hard thing to do because there's so many things you would like to do or want to do, but you just can't. So kind of stinks. I agree. But I'm glad you had a great weekend, Sierra. If you guys are, those of you who are here, I'm going to give it a little more time just to see if anyone else kind of funnels in. You guys can go ahead and get the calendar out and your books open. We're going to be on page 501 today. Page 501. you guys have nothing else to do, go ahead and you can like the video as well. You gotta feed myself, so this is how I make my money with the YouTube. This is my career now. Now that I'm a full YouTuber, it really does go a long way. So then, thank you guys, appreciate it. They've been going down. I don't know if it's I'm underperforming. Maybe I'm underperforming. Maybe I need to pick up the pace a little bit. I need to do a better job. But my likes have been frequently going down, and it's concerning. It's concerning. Okay, about 1 more minute. Hey, thank you guys for the like. I mean, that's very kind of you all. Very, very kind. Okay, let's get started. So, welcome. Happy new week. This is the last week before we get to break. So just power through with me, guys. I appreciate you all being here. 11 o'clock on a Monday. Thank you, all 9 of you. So here's what's going on. Like Tana said, the class breakdown. Things are a little bit different now. So let's take a look at what's going on. So you guys can see on my screen, and if you have it pulled up on yours, you can see the calendar for this week. You'll notice 2 big differences are Tuesday and Thursday. So I talked about this last week that there was going to be this change implemented, and it's officially taking effect this week. There's any more details I'll probably get today. We have a staff meeting, so I'll probably get some more information today. But it looks like this is the format that is going to be school-wide. So it's not just me. It looks like this is going to be how everyone's going to be handling the situation. And so here's the breakdown. Monday and a Wednesday will be math and science for you guys. So math teachers, however they do it, like obviously I'm your math teacher, so what I do is my lecture and then the YouTube video and then an assignment. If your science teacher does something different, maybe they just post a video or they just give you an assignment, whatever it may be. Monday and Wednesdays are dedicated to math and science. So that'll be what you do that day. You're not supposed to work on English, you're not supposed to work on history, any other, I guess, gen eds you have. What are they called? I don't know what word I'm looking for, but any other, like, I guess, arts classes you can think of. You're not doing anything else. All you're doing Monday and Wednesday is math and science. So, like, it's kind of like it's my day to have you guys, I guess. With that being said, then Tuesday and Thursday is history and English, and then I think every other subject, basically. So insert subject here. Anything else you guys are still working on? I don't know what other classes you may be still doing, but any other class will be Tuesdays and Thursdays as well. So that's how the schedule is going to work, which means I'm not going to change anything though from what I'm doing in terms of the stream and like the type of assignment. So I'll still do a stream 11 to 12 Monday, Wednesday, and I'll still have an office hour 1 to 2. So that's not going to change. I'll still be doing that. Again, the office hour is just 1 to 2. That's the live office hour. I'll be available to you guys whenever. Okay, as long as it's before 9, I'll try to get to you. So again, that's just I'll be live from 1 to 2 is the better way to reference that. So this is going to be the new schedule. Now, this is what this means basically. I'm going to be teaching less topics. I'm going to be teaching less content. So my plan is to maybe spend Monday, probably just Monday. I'll go through like a unit. And then I guess maybe Wednesday, depending on how long the unit is, I'll do Wednesday. So like the main lesson portion, the main like content area will be Monday, I think. That's the plan. If I don't get through everything, like today I probably won't get through everything, so we'll pick it up Wednesday. So you'll get some lesson Wednesday. But the idea is you're supposed to only have assignments that are like 30 minutes long. So that's what the administration wants us to do. They want us to give you assignments that only last about 30 minutes. So we're supposed to do our live stream or our videos, however we do it. You guys can learn the material. And even, I don't even know if we're supposed to teach new material, but I think that's kind of discretion of the teacher. And then based off of that, you get an assignment that's supposed to be around 30 minutes or less. And we're supposed to only give you like 2 or 3 assignments a week. So this will be the breakdown of, this is my test week. All right, I don't know if it's going to work out. And I might get more information today, but this is how I plan to do things. We will do our streams Monday and Wednesday like normal. We will have an assignment. That assignment is going to be due. It depends on the assignment, but I'm probably going to make the assignments due at the end of the week. So I can't remember actually what I made Alex do. I can look at it real quick. But you guys should have your Alex should be available to you. I guess I should probably change my screen so you don't see any information. All right. So Alex is going to be, I don't know when I made it due, but that assignment is the idea is you do it, and then Wednesday we'll talk about it. So the plan is that tomorrow you won't do any math. I guess that's the intention. That's what people are trying to do. That's the way we're trying to make this happen. No math is done on Tuesday, which means this. I'm going to teach you guys, and we're going to do a lesson today. We're going to have a great time. Just an absolute blast. You know how it is. And you guys, my hope is that you guys do the Alex today, or at least you start the Alex. At least get a chunk of it done. It's due, it's due on Friday. So it's due by Friday at 3:30. So I would like for you to spend a chunk of time today. Because again, today is dedicated just science and math. So spend your time doing math, right? I didn't make it crazy long. Again, I try to keep it in my head. I know it's different because I'm the teacher, and like for me, timing, it's obviously a little bit different than for you guys'. But it's not too difficult of an assignment. I tried to make it so it was going to be around 30 minutes. That was the intention. It might take some people more, some people less, but that was the goal. Like I was trying to get there. So my recommendation for you guys from here on out is Mondays and Wednesdays dedicated to your math, dedicated to your science. So whatever assignments you get from me and whoever your other teacher is, try to do them on those days. But you will have all week in case things pop up and you can't get them done, or more importantly, if you have questions. Now let me talk about Tuesdays and Thursdays because I won't be live streaming. Okay, I won't have any videos, no lectures, no assignments. If you guys can't do something Monday or Wednesday, you can't get an assignment done, or it's just really challenging to you, please email me. Like I'll still be available to you Tuesday and Thursday. Okay, so I won't have any like live stuff, but if you guys email me, I'll answer my emails. So from all day basically, Tuesday and Thursday. Don't feel like you can't talk to me because it's not a math day. All right, I guess I'm cooperative in that way. Like if you want some help and you're willing to work, I'll give you help. So don't fear that. So I want to make that very clear on those days. Just try your best to make it so you're not working on math those days, because your other classes' expectations, or your other class, are going to not expect you to be doing any other class. So just like on Mondays and Wednesdays, I don't expect you taking all your time doing English when that's supposed to be used for Tuesdays and Thursdays. Okay, the general outline of this week is going to be, we're going to do some 7.7 notes today. Wednesday, we're going to review any questions you guys have on this Alex assignment that's due Friday. So have questions by Wednesday. We'll review any questions you have. And then we'll continue 7.7 notes, and then we'll do some practice as well. So it just depends on where we get to today. We'll continue with it and then do practice problems. And then you'll have this practice sheet that's going to be due Friday as well on Wednesday. So I'll assign this practice sheet. I might actually post that like soon. I might post that like tomorrow or something. Have that up just so you guys can like do it and look at it. If you want to get ahead, you can get ahead. I don't have any problem with that. So maybe I'll post that. I don't know yet. That'll be due Friday. And then Friday, so the idea for Friday is that teachers, there is no day. Like it's not a math day, it's not an English day, it's not a science day. Fridays are a review day. So Fridays they basically said, okay, teachers, you can do whatever you want, just nothing new. So no new material. And from my understanding, no new assignments as well. I don't know if I was 100% understanding of that. Again, I'll probably find that out more today. But it sounded like also no assignments on Friday is supposed to be given. It's supposed to literally just be a review of what you did that week. So what that means to me is it's going to literally just be an office hour. So it's going to be 1 hour from 11 to 12 like we would normally have our stream. It's going to be 11 to 12, and you guys can pop in and ask any questions you have. It could be on the assignment. So like in my calendar, I put review Alex practice and review the practice sheet. It could be that. It could be just a generic question. It could be anything. Anything you want to come in and you want to ask and get more help on, do it. So Friday is going to be a review day. And every teacher is supposed to just be like available to you to review the material that was given to you during the week. Okay? That was a lot. Let me get a drink of water. If you guys have any questions, go out in the chat and type it. On anything. I think also something was released about quarter grades, I think. I might have to get cleared up on that because I don't know if I fully understood it, nor did I look hard enough to try to understand it. But I think if anyone's like really worried about grades or their grades or this situation, I don't know how it's going to be handled. Something I'm sure will be posted pretty soon, or it might already be posted, like on our website, school website or something. Do, 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 do. Going once, going twice. All right. No questions. All right, cool. I know that was a lot. You guys will get used to it. But anyways, this is going to be the plan. So for here on out, this is what I'm planning on doing every week. If you couldn't figure that out, then that means tomorrow and Thursday, no live stream. You don't need to be here at 11. I won't have any live office hours. It's just going to be like a day off from math. But I'll still be available to you. Okay, capiche. Cool. I'm so sick of talking to myself, guys. I'm telling you. I don't know how people do this like as a career all day, every day. It's very challenging. Just like constantly just talking, and I don't know. For all I know, you guys could be just like playing video games and not even listening to me. I could be talking to the abyss. I could be talking to no one. I don't know. No one's commenting. No one's saying anything. I have no feedback. It's kind of painful. That's okay. Just the crazy guy who talks to himself. No worries. Anyways, 501. Go to that page. Page 501. It's written in the chat, so you don't have to be confused. You don't have to ask me. That's what it is. Yeah, I know it's here. I appreciate it. Cool. Just want to make sure you guys are still you're still focused in, you're still listening to me. I'm typing a question in the chat, and the question is, have any of you heard of the symbol E? I can't spell, but have any of you heard of the symbol E? Have you guys ever seen that before in Algebra 1 or geometry or anything like that? Have you ever seen that before? It's a letter. Very good, Tanis. It is a letter. Sarah says yes. Okay, I guess I might need to rephrase that. Yes, it is a letter. That's not what I meant, I guess, in terms of math. So let me ask you guys, where have you seen this in math? Can anyone tell me where you might have seen this in the past? Oh, but in chem, okay. Okay, cool. That's kind of where I was curious, because I was like, I don't think you touch on in Algebra 1. So chemistry, maybe you refer to it. And haven't said forgot what it means. Okay, no problem. All right, cool. So E, this is what we're going to learn about, this base E. You guys know pi, right? Everyone knows what pi is. Pi is 3.14 blah, blah, blah. E is exactly like pi. So what E is a number, is what it is. On your guys' calculators, you guys probably have, let me actually go to my hover cam real quick. Like on your calculator, you guys can see on mine, I have this like symbol E. So you can see like that blue right above the division sign, that's E. So like when I put in my calculator, it just gives me this like value. And it's not a letter, it's a number. So just like they created this symbol pi, it represents a number, the exact same idea here. Instead of pi though, we're calling it E. So that number is approximately 2. So E is approximately 2.718. And now I'm actually going to go to my notes so you guys can type that. So this is 7.7. Title is Natural Logs. First thing I want you to put down is E is approximately 2.718. For the rest of this class, and then a lot of people that will move on into other maths from here on out, whether that's, a lot of people will be in pre-calc, but even farther than that, maybe calculus, calculus BC, however it may be. A really big mistake people make is E, because people forget that it's a number, it's not a variable. That's a big mistake people make. It's a number. So whenever you see the number, well, I guess whenever you see the symbol E, it's representing a number. So from here on out, E is a number. If you guys see me use it, it is representative of a number, never used as a variable. Maybe you think, like right now, maybe you're thinking to yourself, you know what, Mr. Harris, I don't think I've really seen E ever be used as a variable. And that's the reason why, because E is thought of as, well, not thought of, it is a number. Okay, and we call E our natural base. So you guys remember last chapter, we talked about common bases. We talked about common logarithms. So in the chat, tell me guys, what was the common base? What was the common log base? Ten. Very good. Yep, 10. 10 is our common base. So our common logarithm was called base 10. Now we have this idea of a natural logarithm. And our natural logarithm has a base E. And that's written as natural log, in this case, we'll just say x. Okay, we saw a problem like this, guys, in the Alex last week. A lot of people got this, and we went over it, and I explained it briefly. Now we're going to kind of dive in a little bit deeper. So very similar to our common logarithm, you guys can see how I wrote this. So this is a natural logarithm. It's written as ln. So that's not I, that's an L. So lnx. That's natural logarithm. And if I wanted to, I could just put an E right here. It's redundant, so people don't do it. Because whenever you see the letters ln, you know that it's just a natural log with a base of E. Just like a common log, you can write log base 10 if you want, but people know that if it just says log of x, that's just log base 10. Same exact idea, just instead of 10, it's an E. Okay, and this actually might help you to start. If you want to start, I'll probably actually do that when I'm going over some problems, just as a way for us to get used to it, get used to seeing that. Okay. So let me switch the screen over so you guys can see the book. So this is where I'm at right now. Now, there's a lot of like E, the origins of E. We could really get into detail, and if we were together in person, I would definitely take time to like talk about like where does this E come from? Where is this random number? And it comes from somewhere. It's not just 2.718 is made up. Just like pi isn't made up. Okay, pi is a value that's extremely useful, and you guys use pi all the time, but you're probably thinking like, why do we use pi? Where did it come from? And I'm sure you've probably learned where it came from at some point. But it was a number that like was created for a reason. Just like this exponential value, 2.718, this is a reason because it shows up in a lot of different places. And so it showed up so often that they decided to label it as its own symbol, just like they did with pi. So an example they show you at the top of this page is St. Louis Gateway Arch in Missouri is a form of an inverted catenary curve. Catenary curve directs the force of its weight along itself, so that if a rope or chain is hanging, it is pulled into that shape, and if a catenary is standing upright, it can support itself. So just like a special kind of arch. But anyways, the equation for the curve involves E. So an equation to represent this like this big old curve, you have to use the value E. Okay, and E can be used as a base. Here's what I really want you guys to get used to doing. Something like this. It says the function f of x equals e to the x is used to model continuous growth. Whenever you see this, I want you thinking to yourself, this is saying f of x equals 2.718 raised to the x. That's all this is saying. So 2.718 is a number just like any other number. It's just like 3, just like 4.5, just like 7.6. Okay, these are all just values. If your base is a positive value that's bigger than 1, it's being raised to the x, it's going to be exponential growth. For example, if it was 2, 2 squared is 4, 2 cubed is 8, and so on. It's going to just keep growing and get bigger and bigger. That's what we call exponential growth. If there's a negative exponent, it's going to be exponential decay, which we know. We've seen that as well. So just think of it as 2.718. That's all it is. The inverse of E is natural log, and that's what I said here. So let me maybe make that note. Make a note on this. So natural log is the inverse of E. Natural log is the inverse of E. Okay, and then in the book, you guys can see, I think, yeah, you can see, they show you some examples of how natural log is graphed and how e to the x is graphed. So this is like just a really important thing to note. It's not going to be as important right now, but just look at these behaviors. The inverse, or e to the x, is just looks something like a normal exponential we've been seeing, all chapter. It just starts off when it's left to 0, it's very small, and then as it gets right, it gets really big. Okay, the inverse of that is when it gets closer to 0, it decreases very rapidly, and then as it gets closer or farther away from 0 to the right, it slowly increases. Okay. So what I want to start off with today is just example 1. So you guys can see example 1. This is kind of throwing back to what we've done before. Except now instead of using just like random bases and logarithms, we're using e to the x and numbers. So let me go to my hover cam again. So this is going to be the first problem we do, just 1a. And we want to write in log form. All right, so we want to write in log form. Well, what we want to do is we want to be able to take, instead of the log of both sides, we're taking the natural log. Okay, so we're just rewriting this so it's the natural log of e to the x equals natural log of 8. Actually, we don't even need to go that far. What we basically want to do is we can write it as just a new log base. So if you guys remember, what we're used to a lot of times is going from the log into an exponential. We're reversing that process. So if my base of my exponential was e, that becomes the base of my logarithm. The opposite side, that 8, becomes inside of my log. And then we're used to just taking that exponent and just bringing it down. So x. So you have log base e of 8 equals x. Well, we know what log base e of 8 is. It's natural log. So natural log of 8 equals x. If you take that that second step, log base e of 8, think about how we can rewrite this as we can take that, make it our base. So e raised to that exponent x equals 8. Well, that's what I started with. So you can work backwards if that's confusing, if you want to. Okay, so I don't think we need to spend too much time because the only difference now is instead of like a number, we have e. So I don't think we need to spend a ton of time, but I do want you guys to try the guided practice 1 capital A. So go ahead and try that one, guys. And when you're done, just put in the chat you're done. So the answer is to 1 capital A. Okay, guys, type the answers once you get them. I don't know if did anyone not do, were we struggling or anything? Okay, here we go. Natural line equals, all right, thank you. Very good. So you might be able to see a pattern. You might be able to just look at this and know that if you take the natural log of both sides, so if I were to put a natural log here and a natural log here, natural log of e to the x, since they're inverses, cancel out to just give me x. And then the natural log of 9 would stay. Okay, so that's kind of like the shortcut. If not, if you didn't do it that way, you may have written the natural log of base e, or sorry, it should be log base e of 9 equals x, which means the natural log of 9 equals x. So however you decided to look at it, you're going to get the same answer. Again, what you really want to think about is like if we want to reverse an e, if we have something as an exponent raised to something, to get rid of it, you just take the natural log of both sides. That's a really important idea we want to take. And we worked on that with logs, like normal logs, taking the logs of both sides. That was this week's homework, this weekend's homework. Which, by the way, since I forgot to go over it, if you guys have questions, go ahead and stop by my office hour and ask. It's not due till 3:30, I don't think. So, yeah, anyways, that's going to be a very important skill for us. Okay. So, let me see. Let's go to page, I think 503 is where I want to go next. Yeah, let's go to 503. Go ahead and turn to page 503. I think it starts with example 4. I don't think I want to do, let me double check what it is, but I'm pretty sure I don't want to do example 2. Yeah, so example 2, example 2 I'm not worried about. Example 3, guys, on 502, not too concerned about that either. It's using the exact same rules of logarithms. Remember, the rules of logarithms still apply. The natural log is a type of logarithm. So anything we did with a logarithm, we can also do with the natural log. So if you guys remember, we had those properties. We had a product property, a quotient property, and power property. Those can all be used for natural log. The only difference is instead of writing log, you're writing ln. So really no difference. I don't really feel a need to go through example 3 because that's all it's doing. But I do want to do some more practice with solving equations because I think this is going to be like an extremely useful skill for us. So let's go to 503. It looks like this. This is what it's going to look like. So 503, top of the page. Okay, it says equations and inequalities with e and natural log. Equations and inequalities involving base e are easier to solve by using natural logarithms rather than by using common logarithms because the natural log of e equals 1. So I said that before, guys. They're inverses of one another. So whenever you take the natural log of e, you're getting itself. All right, just like if you took log base 10 of 10, you're going to get 1. So that's the exact idea. When your base and your inside of the log are the same, you're always going to get 1. So that idea is going to be very beneficial to us. And you will see why in this first example. Flip the page over. Okay, so this is going to be example 4. Let me get to my hover cam. So they want you to solve 4e to the negative 2x minus 5 equals 3. And we want to round our answer. So we're going to need our calculators for this one. So if you guys have that, go ahead and get those out. I don't even know if you'll need them right now, but when I give you a guided practice, you're going to probably need them anyway, so. All right, so solving equations. Guys, we know that nothing changes when solving equations. Even though we have these logs and like these weird things going on, nothing changes. At the end of the day, the goal is we got to get x by itself. So that's still got to be our mentality. If we're solving anything, at the very least, we can always just at least isolate x, or try to. So the first step to doing that is to get the constants on one side. Meaning I have to add 5 to the other side of the equation. And that's the first step I'm very confident you can all do. So add 5 to both sides. I get 4e to the negative 2x equals 8. Okay, again, the next step that's pretty obvious is divide by that 4. So get rid of that 4 to the other side. So I get e to the negative 2x equals 2. 8 divided by 4 is 2. Okay, so we can make some progress. So regardless of how comfortable you are with natural logs, at the very least we can make that much progress. Now this is where we have to be a little bit more creative. So what I want to do is I need to get this x out of the exponent. I need to somehow find a way so this gets put out in front. And we can do that by using the property, the power property. All right, so check this out. I could take the natural log of both sides. So I take the natural log of e to the negative 2x equals the natural log of 2. Since this is a logarithm, I can use the property of the power, or the power property. So I can take that exponent that's inside the log and throw it out front. So I get negative 2x times the natural log of e equals natural log of 2. Okay, hopefully you guys are following. Now, if I were to, I might as well show you guys, just so if you don't believe me, but these are inverses of one another. So think to yourself, like what do you expect to see when I plug in this? Natural log of e. You see there's a little glare to it. Yeah, if I put in natural log of e, like what would you think we would see? So hopefully your head's going to 1. I press equals and bam, I get 1. All right, which means that my natural log of e is right here. That's equal to 1. So I'm left with just negative 2x equals natural log of 2, which means x equals the natural log of 2 divided by negative 2. On my calculator, I have a button for natural log. I know Desmos has a button for natural log, so I might as well just go to Desmos real quick. Show you guys my screen. Might as well go to Desmos. That's what you guys will mostly be using. And they wanted you to get a decimal approximation. So let me type in here natural log of 2. So all you have to do is put ln 2. Desmos will know what you're doing. And then divide it by negative 2. And so my approximate answer, and they wanted that rounded to what? Nearest 10,000th? Negative 0.3466. There's your final answer. Okay, that's the process we want to go through. So any questions you guys have, go ahead and throw them in the chat. Again, I'm like a broken record, but we're not changing how we're solving these problems. This is just like what you guys did over the weekend as your practice. This is just what we've been working on. Only difference is the fact that instead of writing log, we're writing natural log. And just have to understand that the natural log of e is equal to 1, which you guys will have calculators, so you can always double check that. Sierra says no. Okay, good, good, good. Anyone else have any opinions? Comments, concerns? All right. Take that as a no. So I want you guys to try guided practice 4A. So go ahead and give that one a go. See if you can get that answer. They want you to round to the nearest 10,000th. So make sure you guys do that. Guided practice 4, capital A, round to the nearest 10,000th. And then write your answer to 4A below when you're done. All right, Sierra got an answer. Looks good, Sierra. Round it to the 10,000th, so give me one more decimal point, but yes, you're right on track. You got it. Good job, Sarah. Okay, very good. I'll give you guys about 1 more minute, 2 minutes. Okay, so let's take a look. I'm assuming if you hadn't got it quite yet, maybe you got stuck at a step, so let's take a look at it. So we have 3e to the 4x minus 12 is equal to 15. All right, so that was given to you. So what we want to do is we want to add 12 to both sides. So I get 3e to the 4x equals 27. And then I want to divide by 3. So I get e to the 4x equals 9. Take the natural log of both sides. So I get natural log of e to the 4x equals natural log of 9. Use the power property to get 4x. So again, I'm taking that 4x and throwing it out front using the power property. So I get 4x natural log of e equals 9. The natural log of e is 1, so 4x equals natural log of 9, which means x equals natural log of 9 divided by 4. And if I put that into Desmos, see if you guys are right. Yep, 0.5493. Here's your answer. All right, how do we feel about this? Would you guys want another practice problem? All right, cool. Let's do another one. We're going to do example 5 now. So we're going to work the other way. All right, so these ones you guys have been given an exponential. So you've been given e to some power. Now we're going to start with the natural log. Okay, so we're starting with natural log and we have to find x. So we have 3 times the natural log of 4x equals 24. All right, so what do we want to do? Well, first thing I want to do, divide by 3. right? We might as well get rid of that 3. So I get the natural log of 4x equals 8. Now this is where it gets a little tricky, all right? Because I don't know off the top of my head what inside this has to be to give me 8. So somehow I have to get rid of that natural log. I have to get rid of that natural log. How do I do that? Now we're reversing what we were doing. So before we were saying, okay, given an e, we would take the natural log of both sides. Now we're going to make e a base of both sides. So instead of taking the natural log of both sides, we're basically taking e of both sides. Because if the natural log of 4x equals 8, then that means e to the natural log of 4x equals e to the 8. Well, e to the natural log of a number, you're left with just the number. So e to the natural log of 4x is equal to just 4x. Which means x equals e to the 8th divided by 4. Pretty confident you guys can all use calculators. So you throw that into Desmos and you get 745.2395. Okay, very, very similar process. Same idea. You want to get all the constants on one side, isolate x, and then after you isolate x, you have to use an idea of properties of logarithms. In this case, instead of taking a natural log of both sides, because we already have that, we take e of both sides. All right, let's see if that makes sense to you guys. Try guided practice 5, capital A. And this will be the last question of today. So we'll finish up with this. And then put your answers in the chat when you guys get them. Okay, a couple different answers. Take about 1-2 more minutes. So Sierra got a 0.8255. Sarah, did you get 1.2383? Tanis also got 1.2383. Here they go. Okay, so we're split. All right, so I'm going to go over this now, and I want to see some feedback from you guys. Those of you who end up getting it wrong, I want to know what step you might have messed up on. So first things first, divide by 5. So I get the natural log of 6x equals 8/5. Because it's this situation, there's nothing else for me to do. I want to make e the base of both sides. So it becomes e to the natural log of 6x equals e to the 8/5. Which leaves me with 6x equals e to the 8/5. Meaning x equals e to the 8/5 divided by 6. Okay, and you go into Desmos. You type in e to the 8/5 divided by 6, and you get 0.8255. All right. So let me hear from Sarah and Tanis. What did you guys do? How did you guys get 1.2383? Was there a certain step that was a little bit different? Let me see if I can help you out. I used the wrong number. Okay. All right then. Well, guys, Alex is gonna have plenty of practice. Just miscalculated. Yeah, understood. So Alex is gonna have a lot of practice with this stuff for you guys. I think we got through everything you need to complete your Alex assignment, so you should be good with that. Please, like I said, take today and try to do that. I'll be here from 1 to 2, so if you guys want to hop in, work on Alex, ask any questions as you go, feel free. Today's the math day, so it's due Friday, but better get it done early. You might as well while it's fresh in your brains and everything. So just let me know. Hope you guys have a great rest of your day. Is there any questions you guys have, anything you need from me? Yeah, you too, Sierra. No problem. I appreciate it. Thanks for stopping by, guys. I really do appreciate it. Hopefully it's helping. I'll keep you guys updated on anything else I hear with the scheduling and quarter 3 and all that good stuff. So as we go, I'll let you guys know. All right, looks like we are good. I will see you guys. If you, like I said, if you want to stop by late, I'll see you. If not, I'll see you Wednesday. We will pick up our live stream. All right, take care.